Welcome back. Today, a fiber optic link budget. The same kind of engineering accounting we did for microwave, but now with light traveling through glass. Here is the setup. A laser transmitter outputs 10 dBm of optical power. Its output goes through a connector into the fiber, which loses 1 decibel. The fiber itself is 100 kilometers long and attenuates 0.3 decibels per kilometer. At the far end, another connector loses another 1 decibel before the light reaches the receiver. The receiver's sensitivity threshold is -60 dBm. We have 5 questions. Part A. Find the optical power delivered to the receiver. Part B. Compute the power margin. Part C. Find the maximum fiber length that still gives a 14 decibel margin. Part D. Will a 300 kilometer link work? Part E. Would a 50 kilometer link be a good design choice? Before we plug in numbers, let me show you exactly why the dB arithmetic works. This is the proof that explains why dBm minus dB plus dB gives dBm. In the linear world, a cable or a connector does something simple. Output power equals input power times a loss factor. If a connector lets 80% of light through, output equals input times 0.8. Pure multiplication. Now take 10 times the log base 10 of both sides. Log of a product is the sum of logs, so 10 log of output equals 10 log of input plus 10 log of loss factor. In dB notation, that is simply output in dB equals input in dB plus loss in dB. Multiplication in linear becomes addition in dB. That is the whole trick. Now about units. dBm is defined as 10 log of power divided by 1 milliwatt. It is a log of a ratio, but reference to an absolute 1 milliwatt. So dBm already is power in log form. dB by itself, like a cable loss, is 10 log of a dimensionless ratio. Add them. dBm plus dB equals 10 log of power ratio plus 10 log of another ratio equals 10 log of the product, still dBm. Subtract, same thing in reverse. The units stay absolute because the reference milliwatt never disappeared. One warning, you can never mix linear and dB. 10 milliwatts minus 14 dB is nonsense. One is a power, the other is a log. If you need to convert, go back to linear first, then do the math. Now we apply this to the fiber link. Here is the full link laid out. Transmitter. Laser at plus 10 dBm. Immediately the light passes through the laser to fiber connector, minus 1 dB. Then it enters the fiber, 100 kilometers of glass. At 0.3 decibels per kilometer, total fiber attenuation equals 0.3 times 100, which is 30 decibels of loss. At the far end, another connector couples the light out of the fiber into the receiver, another minus 1 dB. Everything in dB, everything adds up. And that is how every optical link budget is read, like a running total from laser to receiver. Part A. Optical power at the receiver. Start with 10 dBm. Subtract 1 dB for the laser connector. 9 dBm. Subtract 30 dB for the fiber. -21 dBm. Subtract 1 dB for the receiver connector. -22 dBm. Received power equals -22 dBm. That is about 6 microwatts reaching the photodetector. Way down from 10 milliwatts at the laser, but absolutely detectable with a sensitive receiver. Part B. The power margin. Margin is the difference between what we have and what the receiver needs. Margin equals received power minus sensitivity threshold, -22 dBm minus -60 dBm. That is 38 decibels of margin. 38 dB is a factor of about 6,000 in linear power. In fiber engineering, 15 to 20 dB is typical, so 38 dB is an extremely healthy margin. The link is well over-engineered for this distance. Part C. How far can the fiber go and still keep a 14 decibel margin? We target a received power of -46 dBm. That is the threshold, -60, plus the desired 14 dB margin. Now we set up the budget. Laser output minus the two connectors minus fiber loss equals target power. 10 minus 1 minus 0.3 times length minus 1 equals -46. Rearrange. 0.3 times length equals 10 minus 1 minus 1 minus -46, which is 54. Length equals 54 divided by 0.3, which equals 180 kilometers. So this system can support up to 180 kilometers of fiber while still having the 14 dB safety cushion. Almost double the original 100 kilometers. Parts D and E. Quick judgments, then 3 takeaways. Part D. 300 kilometers? 0.3 times 300 is 90 decibels of fiber loss alone, plus 2 decibels of connectors is 92. 10 dBm minus 92 is -82 dBm, far below the -60 threshold. The link does not operate. You would need amplifiers along the way or a more sensitive receiver. Part E. 50 kilometers? Loss is only 15 decibels of fiber plus 2 of connectors, 17 total. Received power would be -7 dBm, 53 decibels of margin, massively overspecified. The link works, but you paid for a laser and receiver you did not need. It is a design mismatch. In engineering, we choose components to fit the distance, not overshoot it. 3 takeaways. 1. Every element in a fiber link is a dB addition or subtraction. Start with transmit power, walk through the chain, end with received power. 2. Margin is your friend. 10 to 20 decibels covers aging, temperature, and manufacturing variations. 3. Match the hardware to the distance. Overspecified links waste money. Underspecified links do not work.